Every night we look up and see it, calm, familiar, eternal, the moon. It has guided our sailors, inspired our poets, and set the rhythm of our life since the dawn of humanity. It feels like an unbreakable constant. But what if I told you that the moon is not a stable companion? That it is, right now, slowly, silently, drifting away from us. Not metaphorically, literally. Each year, our moon moves about 3.8 centimeters farther from Earth. That's roughly the speed your fingernails grow. A tiny, imperceptible movement. Yet, over billions of years, this subtle, relentless motion will completely reshape our planet. Our days will stretch longer, our tides will vanish, and one day, the perfect, delicate dance between Earth and Moon, the one that stabilized our world and made life as we know it possible, will simply come to an end. This is the incredible 5 billion-year story of how the moon is leaving us, and what happens when our faithful companion is finally irrevocably gone. How we know the moon is drifting. So how can we be so sure of a movement so small, happening so far away? The answer lies not in ancient prophecy, but in a leftover from the space race. During the Apollo missions in the late 60s and early 70s, astronauts didn't just collect rocks. They left behind a series of remarkable relics. Small, highly precise laser reflectors, essentially mirrors, on the lunar surface. Today, powerful observatories on Earth, like those in Texas and France, fire intense laser beams at those Apollo mirrors. The light streaks through space, bounces back, and by measuring the precise time it takes for that round trip, scientists can determine the exact distance between Earth and the moon, down to a breathtaking few millimeters. By repeating this experiment, not for days, but for decades, researchers discovered the undeniable truth. The moon is steadily receding at about 3.8 centimeters, or 1.5 inches per year. But why is it happening? It's caused by a spectacular, ongoing exchange of energy called tidal friction. As Earth spins, the moon's gravity pulls on our planet, creating those enormous bulges of water we call tides. But because Earth is rotating so much faster than the moon orbits, that tidal bulge actually leads the moon slightly. This forward bulge acts like a massive gravitational slingshot. It gives the moon a tiny, constant forward tug, a boost of energy, gradually pushing it outward into a higher orbit. It's an exchange that perfectly balances two fates. The moon gets farther away, and in payment, Earth's rotation slows down, making our days longer. The cosmic dance continues, fueled by the very water in our oceans. The slowing clock, what happens to our days? To truly grasp this effect, we have to look back to the beginning. Roughly 4.5 billion years ago, after a massive, world-shattering collision between the early Earth and a Mars-sized body named Theia, our moon first formed. It was a chaotic birth, and the moon was a close neighbor, perhaps only 22,500 kilometers, or 14,000 miles away. Back then, the physics of tidal friction were magnified by that close distance. A day on Earth lasted a mere 4 to 6 hours. The tides were terrifying, hundreds of meters high. They scoured the land, reshaped continents, and stirred the oceans like massive planetary mixing spoons. Today, after billions of years of this braking action, Earth's rotation has slowed to a manageable 24-hour day. But this deceleration hasn't stopped. In the far, far distant future, hundreds of millions of years from now, Earth's day will stretch to 25, 26, even 30 hours. Imagine sunsets that creep by twice as long, nights that could last for a week. A slow, almost dreamlike rhythm replacing the urgency of today. This isn't just a poetic idea, it's a profound shift in how our planet functions. Longer days would fundamentally alter global wind patterns, ocean currents, and climate cycles. They would change the timing of photosynthesis and every biological cycle that evolved under a 24-hour clock. Our world would become a place governed by a slower clock, completely alien to the one that governs us now. The tides begin to fade. For all of history, the moon has been the primary driver of Earth's tides. Without it, our oceans would still move, pushed by the sun, but their power would be dramatically weaker, reduced to maybe half their current height. As the moon relentlessly recedes, its gravitational pull on our water weakens. Tidal ranges shrink. This seemingly minor change delivers a knockout blow to entire ecosystems. Coastal habitats that rely on the daily inundation of strong tides, like vast mangrove forests, nutrient-rich salt marshes, and complex tide-fed estuaries, will begin to collapse. The very engine of these coastal nurseries will sputter and fail. Furthermore, scientists believe that ocean circulation patterns, which are crucial for distributing heat around the globe, could slow down. This could intensify global weather extremes, creating a very different and potentially more volatile climate. In the short term, meaning the next few million years, we won't notice much. But give it 500 million years and our coastlines may become eerily, unnaturally still. But the most critical loss is not just the water's movement, it's the loss of the moon's silent, essential service: global stability, the moon's role in Earth's stability. Our moon is far more than just a light in the night sky. It is Earth's gravitational anchor. It's the sheer mass of the moon and its orbital distance that keep Earth's axial tilt, that 23.5-degree angle that gives us our beautiful, predictable seasons, relatively stable. Without this massive stabilizing force, Earth's tilt would start to swing wildly. Calculations show the tilt could change between 0 and 60 degrees, sending our climate into absolute chaos on a timescale of millions of years. Imagine the extremes: a 0-degree tilt. The sun would hang directly over the equator year-round. Seasons would vanish. Polar regions would freeze permanently, while the tropics would become scorching deserts. A 60-degree tilt. The Earth would essentially be spinning on its side. Equatorial regions would experience long, dark winters and blinding hot summers. This isn't theoretical doom-mongering. Mars, with only tiny, insignificant moons, suffers this very fate. Its axial tilt can change by tens of degrees over a few million years, constantly transforming its climate. As the moon retreats, Earth's overall stability weakens, compromising the very predictability that allowed complex life, and eventually intelligent life, to thrive. Our companion made the 23.5-degree sweet spot possible, the final horizon 2 billion years hence. Let's fast forward a few billion years. The moon is now twice as far away as it is today. It will appear much smaller, perhaps half its current size in our sky. The cosmic, once-in-a-lifetime coincidence of solar eclipses, where the moon perfectly blocks the sun, would vanish forever. There would be no more totality. Earth's rotation has slowed dramatically. One day might last a grueling 45 hours. Tides are nearly imperceptible. The lunar month itself has stretched, drastically changing the biological and perhaps even cultural cycles that evolved in perfect lockstep with the nearby moon. Eventually, if time were infinite, the Earth and moon would reach their final destination. The energy exchange would stop, and they would become tidally locked. Earth would show only one face to the moon, and the moon would orbit in perfect sync with Earth's rotation. The long, slow drift would finally settle into balance. But the cosmic curtain may fall before that balance is ever struck. By that point, in about 5 billion years, the sun itself will be in its death throes. It will begin expanding into a monstrous red giant star, swallowing the inner planets. The moon's slow dance may not end in quiet separation, but in a final fiery embrace with an expanding star, a catastrophic event that will utterly consume both worlds. Why this measurement matters. You might be asking, why dedicate decades of research to something happening so slowly, on a timescale so impossibly vast? The answer is that understanding the Earth-Moon relationship is key to understanding habitability across the entire universe. The Moon is a textbook example of a stabilizing force. Exoplanets with large, stabilizing moons may be far more likely to retain a stable climate, giving life the long, uninterrupted chance it needs to evolve. Some scientists even posit that without our Moon and the conditions it created, intelligent life might never have emerged here. On a practical level, every laser pulse sent to those Apollo reflectors contributes to our most rigorous understanding of gravity and space-time. These precise lunar measurements help refine spacecraft navigation, deepen our grasp of celestial mechanics, and even allow us to test Einstein's theory of relativity with unmatched precision. Every ping is like a heartbeat, a reminder that this gravitational relationship is alive, evolving, and ultimately finite. The long goodbye. So yes, the Moon is leaving us. Slowly, silently, and inevitably. It has been our companion since Earth's fiery beginning, controlling the rhythms of our tides, inspiring our myths, our love songs, and our greatest acts of exploration. Someday, far in the future, it will be so distant that Earth's nights will grow markedly darker. The mighty pull that once shaped oceans and dreams alike will fade into history. But for now, it is still here, still shaping our world, still drifting just a little farther away each night. Go outside tonight. Look up and appreciate the long, slow goodbye of our one true companion. If this video made you see the Moon in a whole new light, hit that like button and subscribe to Cosmic Crunch, where we explore the mysteries that make our universe both beautiful and fragile. Drop a comment below. What do you think life on Earth would be like without our Moon? And stay tuned, because next time we're diving into a story even stranger, about a planet that glows in the dark